So the basic thesis here is that scientists represent our world into artifactual models. They're man-made, they're not just found, they're man-made. They're typically mathematical, statistical, or diagrammatic. Those small worlds become autonomous working objects, and the working objects is what I want to focus on today, the qualities of working objects, and that those working objects are used in various kinds of knowledge production. There's two main dimensions. One is to inquire into the world inside the model, so the world is represented in the model, and a lot of economics is about inquiry into that small world posed in the model. And a lot of that work is primarily theory development work. It's figuring out the limits of the theories, figuring out the constraints built into the theories. It's figuring out what those theories that we've instantiated tell us about the way we've figured about them. Much more problematically, those small world models are also used by economists to help think about the big world, the world that they are taken to represent, and also sometimes used to, not just to understand that world, but to think about intervening. Now, of course, not all models in economics are what I'm calling small world models. I'm mostly talking about those mathematical models you find in a lot of mainstream, particularly micro, but some macro. So not all models in economics are going to be working objects in the way I suggest. So I'm not talking about great big macro models, which I think of rather like climate science models. They're trying to model everything at once. I'm not talking about econometric models, because by and large, although I will talk about one of them, I'm not talking about models that have an empirical end, a statistical end, which would give you that potential match, which would tell you about the world. So when I'm talking about a technology of objects which help you think about the world you live in, I'm talking about that as a kind of casual empiricism rather than anything strict and definite and well measured as in econometrics. So I'm trying to capture something which I think is not just true of economics, but is true of a number of other disciplines now. I was recently at a meeting of veterinary scientists, or animal scientists, and there were people there who said they had a PhD in modelling. And I couldn't figure out what that meant. But in their community, that's what you have. You have a PhD in modelling, and you just happen to be in an animal science. But they've even lost you don't have a PhD in economic modelling, you have a PhD in modelling. And these are people who have learnt modelling techniques which they take across borders between physics and biology and maybe economics. So I'm talking about that kind of activity, the modelling activity. And I'm particularly interested in this talk in what kind of qualities working objects have. What kind of qualities do models need to have that make them into good working objects that are going to give us this technology of inquiry in sciences. And I'm starting off from a very nice discussion by Lorraine Daston and Peter Gallison about the history of objectivity, but in this case, they're talking about working objects. Working objects can be atlas images, type specimens, or laboratory processes. And I've highlighted the things I think are important. Any manageable and communal representatives of the sector of nature under investigation. Basically, science can't do science if it has just a whole lot of particulars. You need some kind of working objects which have standardized this chunk of nature you're trying to think about. Otherwise, you don't know whether you've just got a one-off particular or whether you've got something that's going to give you some more power. So it's that standardization, and standardization isn't the right word here for us, for me, but it's something about being able to represent at a level of a class, not being a single individual case. So standardization can mean something like the form of maps. Manageable means something we can work with. Communal means it's going to be something that is shared across the community or within a set part of the community. Very typically when we think about economic models, there are shared objects that people are going to argue over and develop and so forth. So what qualities, taking these as a sort of starting point, what qualities make models good working objects for science? They need to be manageable. That means, as far as I can see, is they need to be small enough for you to work with them. One of the reasons that some big macroeconometric models disappeared was because by the time you get to a certain number of equations, they're not manageable in terms of the kinds of ways I want to talk about manageability. So they're manageable, small in relation to the cognitive abilities of the scientists. Their working objects means that they must be objects that you can work with. And I mean something more than Daston and Galison here, because for me that means they've got to be workable. You've got to be able to do something with them. They're not just type specimens of a finch, as Darwin might have had. They're things you can actually manipulate. In order to manipulate them, you've got to have you've got to have resources in them that can be worked with. So they're not just working objects for me, they're workable objects. Okay? They're not just objects I, as a scientist, can work with, they're objects I'm going to do work with. They have to have capacities to reveal. And I want to focus something which I didn't talk about in the book, but something I've been thinking about since, which is the number of dimensions that are in a model that give you the capacity to reveal. So that's another aspect which I think is here. And the final one here is to be justifiable as typical or exemplary, that is, representative in some way. So I'm thinking about this representative power a bit in the way that, for instance, the Daston and Galison type specimens, that's so not just any dead finch, but one that represents the type of finches that you're interested in. So something about these working objects needs to have representative power. Okay, so now most discussions about models talk about representations. Well, something can be a representation of something and have representative qualities at the same time. So I'm not trying to say it's representatives rather than representations. I'm trying to say that our representations may have, in certain cases, a representative quality as well. So I'm wanting to capture the representative quality that makes them into working objects. So particularly the obvious one that one would think of in science are model organisms. That's the fruit fly, the zebrafish, whatever the yeast is that's endemic. Those objects which biologists pick out as being the objects that the organism that's going to represent a particular class of things. Fruit flies for insects, lab mice for mammals, whatever it is, there's always a particular organism that's picked out because it has representative power for other mice, but also possibly for mammals as a class. So the idea with the representatives is you can find a representative, then you can explore the representative, you can explore the fruit fly for its genetic qualities in order to tell you something about something more general, genetics in general. And it's the representative power that gives you that possibility of moving from the specific to the general. So let me talk about these in turn. Now, I get criticised by economists for calling these things called small. Actually, don't mind small, but they hate little. I don't know quite little is pejorative, but small seems to be okay. And the point here is that the classic critique of models is that how can they possibly tell you anything about the world? Look how small they are. They don't really have enough content. And look how false they are. They don't represent anything that we think really goes on in the world. So it's a kind of classic problem that then they don't represent in a way that is going to be any use for you. And part of that critique is smallness. I think this is kind of an unhelpful place to start with because it tells you what models don't do rather than what models are potentially doing. Right? So if I'm thinking about what models might be like, I want to say that models are not necessarily simple, small, simplistic or toy-like. They might be, right? But they're not necessarily just going to be completely useless because of their size. And I think the way to think about them is to think of them as miniature or compressed worlds. So my idea of a world in the model is not that it's just a small, simple one, but it's being compressed down, a bit like when you cook a sauce and you reduce it down. You know, it's a kind of focused, intense account of something. So I want to explore this a little bit by coming at it sideways, because I think it's very often difficult to get out of this critique problem here. Think maps, well, maps is a kind of a standard thing to think about as a comparison, and I very much like the paper that Diego and, who was it? Diego. And Herman did this, which is a very nice paper on maps. So models as maps, so just read this paper and you get it all. But the point is that, well, as they say, not every detail is given, but you're going to exhibit the relations you can't grasp by eye, and that they're really useful objects that get around the world. They're miniaturized accounts of the world. And you can have bad maps and silly maps and simple maps which don't tell you anything, but of course most of us who like maps think that they can be really useful, and they're in this miniaturized version of the world. Poetry is a much less obvious thing to compare scientific models with, but I do think it's worth thinking about. Here's another small, potentially very small form, and the reason I like poetry is because it's very formal. A lot of poems have a very particular form and have to be expressed, whatever is expressed has to be expressed according to these very strict forms. So thinking about what models can be, as opposed to this critique, they can be miniature compressed worlds of the kind of descriptions, the kind of things we have in maps and poetry, small enough to be manageable, but spacious enough within their boundaries to actually represent or reveal or give us some insight. And here's one of the examples of maps I often work with when I teach. It's the very famous set of maps of London. It's a social scientist map of London because it's based on a large survey of the poverty of the households in London, street by street. And it also shows two of the big new stations that were built in the mid to late 19th century on the edge of London, King's Cross on the right and St Pancras on the left. Well, one of the things about stations is if you're inside them, it's really difficult to get a handle on where things are on the size. It's actually quite helpful to have a map because then you see the relationship of the parts. But this map reveals a whole lot of things about the social class structure of London because the survey is being turned into a map, and the map reveals a lot of information which you couldn't get from a table or just by going through all the details of the survey, because it's a way of, it's a working object to express lots of information you already have. So maps are like models in that they are small worlds, they're manageable by construction, they omit certain things in order to make it possible to put them into the right scale. Again, they're dependent on purpose. They have abstractions, they denote things in certain ways, and they have sort of simple colour coding to help you figure out. But social science maps give you, they don't tell you something you couldn't have known by any other way, but they certainly reveal it in a way that probably makes it much clearer than if you had to, as it were, read through a table. Here's poetry. These are haikus, Japanese form of poetry, which are very small and extremely strict in their requirements. Extremely strict. About the sort of smallest, strictest form I think there is. So these are early ones in the 1600s. And the point about these is they're really, really, really compressed accounts. My usual version is a sonnet, but I can't get 14 lines on a page. But sonnets express this similarly. You know, you've got 14 lines, the rhyme structure has to be such, the metre has to be such. There's two different forms, they both go back to the 13th or 14th century. If ever there's a formal object which you has to obey certain rules, it's a poem. These kinds of poems. And I had this sort of insight about this smallness in poetry by listening to, we have a company called the Poet Laureate in Britain, who's the official poet and has to write official poems on official occasions. But she was being interviewed, and the interviewer said, you know, you write very small poems. How do you manage to express anything? They're so small. And she said, this is a really strange way of thinking. Even in a very small poem, you can express, there's a lot of space within a small poem. If you are articulate enough, you can express lots of things even in a small form. So smallness doesn't mean smallness, meanness, it means space within which you can articulate something. And for my purposes, they're really neat because they have this very formal rule-like structure, just like a mathematical model. I hope you're not completely offended by this comparison, but here, okay, so small worlds doesn't mean that they're mean, useless, silly. They can be expressive and they have articulate space inside them. Okay, the second point, second thing we need to get these objects to be working objects is workability. To have workability, you need resources for investigation. It needs internal resources to make them into objects of investigation, means of inquiry. And what I'm arguing here, which I think is something which wasn't part of my thinking when I was doing the book, was that workability depends not only the possibility of manipulability, but the possible dimensions which can be manipulated. So thinking about the space inside a model, the size of a model, one of the things to look out for, I think, is the dimensions of the things that can be altered in working with this model. And I want to say that workability is not quite the same as reasoning. So this is where we begin to see the difference between maps and poems and these small world working objects representations. So maps can be revealing, but they're not necessarily going to be workable dimensions. Here's a 3D model. It comes from a little children's playground. It's quite charming, but it doesn't move. There's no working resources there. It's just a 3D. So the dimensions is not just the number of dimensions, but also the workability. So three dimensions is better than 2, maybe, for what you want, depending on what you want to do. But it also needs some possibility of these people actually working here. Here's possibly the most famous map in the history of cartography, which some of you may have seen before. It's a map denoting Napoleon's Moscow campaign. And it's a two-dimensional object, but it expresses 6 dimensions. The big fat line, sandy-coloured line, is the French soldiers setting out for Moscow from Paris, and the black line is the soldiers coming back, or the lack of soldiers coming back, as the soldiers fall prey to disease, cold, I mean, all sorts of things apart from battle. So very few of them actually make it back. So represented on this map, depending exactly on how you count them, is the size of the army and the changes in it, their positions, there's a latitude and longitude, there's the direction of travel, there's the location of dates when these things happen, and there's the weather. Right? So this reveals a huge amount about Napoleon's Moscow campaign. Right? So it's a small object, 2 dimensions on paper, representing 6 dimensions, a revealing object, but not one that you could reason with in a kind of counterfactual way. You could say, well, suppose the weather wasn't that bad, or suppose they'd taken this route. So you could think counterfactually about it, but you can't, as it were, take out bits and plug them in and do things with them. So it has a limited workability in my sort of terminology. Here's a couple of models which are things I think do have workable resources. The one on the left is the famous Tableau Économique of François Quinet in the 1760s, which is an account of the circular flow between farmers, landowners, and manufacturers. And there's numbers on it, and you can use the basic model with different numbers and different flows to explore whether or not this model of the economy, of the circular flow in the economy, what would happen if you put different numbers in. And we know that's what he did because we have the evidence of sets of different numbers in the bottom line, the top line and the bottom line. The one on the right is in some ways similar, but in the same kind of domain. It's a current model that a development economist might actually wouldn't take with him as he went around Africa or wherever it is. He'd get the local carpenters to make this. And the idea is that it represents the river flow, the flow of water through a terrain, and the little sort of square boxes with holes in are fields, and you set the whole of ball bearings going, or balls going down it, and they settle in the fields. So the farmers who have the fields at the top get lots of water, and the farmers with the fields at the bottom get poor water. And this is typically used by making the farmers who are rich farmers at the top with lots of water play the farmers at the bottom, and vice versa. So it's a model used to get the community to think about how to share water resources. Okay, so it's a it's a workable model in that sense. And you can change the flow and do various things. So this is the kind of thing I mean when I'm talking about workable resources. It doesn't have to be bits of mathematics, doesn't have to be bits of algebra. And the third thing I think one needs is this capacity to reveal. That depends on the technology of inquiry. So I want to say something about the technology of inquiry. For me, it's really quite important that one thinks about this as a technology of experimentation. So it's a form of experiment. The way that models are used, which is for me more important than what models are, is as a form of experimentation. And I'm using Roman Higgs' 1997 account of models as having an internal dynamic given by these workable resources. So if we think about the internal dynamics here, they're the qualities of stuff inside the model that one can ask questions with and change and alter around. But in order to get that project going, you have to have an external dynamic. You have to have a question and a purpose that you're trying to ask about this model. So you need an external dynamic, which is what's going on here if I do X. An internal dynamic, which is the workability of the model, will give you some answers. But that only gives you answers within the world of the model. So there's like a glorified thought experiment with a manipulation of the model. And then there's the really difficult bit: can you make inferences from that experiment? Under what kinds of ways can you make inferences? Well, you can make inferences within the world of the model very easily, because you've created this world, and you've created these manipulatable resources, and you've asked a question, you've got some answers, and you've got an inference regime inside there. But the big problem is always relating those inferences to the world outside. So it's not that making this an experimental framework gives the answers. It's merely that it gives a way of framing this problem about how you relate the model to the world, is to think of it as fundamentally an inference problem rather than some kind of basic similarity difficulty. It doesn't solve it, it just frames it differently. Okay, so this technology of inquiry that I'm interested in here, and I want to... I completely lost track of time here. I want to just briefly go through three different models to show you this: questions, models, manipulations, and answers. And I've got three models of roughly the same period, one of which is an algebraic model, which is an inquiry into the world in the model, quite clearly. Another of which is a statistical econometric model, which is inquiring really about the world rather than the model. And the third one, which I talked about on Tuesday for some of you who are here, is about a model which tries to be in both domains. This is a really straightforward little model that Samuelson built to understand Keynes's general theory. Well, actually indirectly, because he took it from Hansen. So this is on the top left, the basic Keynesian, Samuelson's basic version of Keynes's general theory into a little model. Y equals G plus C plus I, and then each of Y and I have been, C and I have been further set out. And what he does with this model is to inquire what kind of answers this Keynesian model would give us about what happens if we increase government expenditure. That is, we have a Keynesian policy intervention in this little world, what will happen? And the first thing he does, having got his little model, is to simulate it arithmetically by putting in some maybe plausible, maybe not plausible values for alpha and beta. And I'm not sure whether you can see these numbers at back, but just changing these numbers gets completely different kinds of answers out in these model simulations. So some of them have an increase which then just basically levels out. Some of them create big cycles, some of them create damp cycles, some of them create exponential, off out into the explosive stratosphere. And at that point, he said, these simulations, these experiments, reveal almost anything can happen. You've got this small little standard Keynesian model, and depending on what numbers I put in, anything can happen. And this is not very satisfactory. So he then went ahead and solved the model algebraically and plotted all the solution space according to what kinds of outcomes will happen in what kinds of spaces. So he sort of mapped those possible outcomes into a map of all the possible solutions that you could get. So this is clearly an inquiry into the world of the model, inquiry into Keynes's model, well, Keynes's theory translated into a working object of a model, as to what would happen if you actually did increase government expenditure by 1 unit. This is one of Tinbergen's models for the Great Depression. Tinbergen built the first ever econometric models, macroeconometric models, rather. On the left is his Dutch model, in equation form, having been estimated. On the right is actually not from the Dutch model, but from his American model, a chunk of one of these equations showing you what happens over time once it's been fitted. And in the middle, there's a little causal arrow sequence of the time relationships in the model. So what are the questions here? The questions are, how should the Dutch economy get out of the Great Depression? It's 1935, 1936 when he's building this Dutch model. And he simulates the Dutch model to see what the Dutch economy, what the Dutch government should do. And his answer is they should come off the gold standard, and then they would solve their problem. Which indeed they did, but not for a long time, and not because Tinbergen said that, but because Tinbergen was very, very junior. But the point is that the inquiries, the questions about the model, were not questions about how this model behaves like the Samuelson ones. They're questions about what can this tell us about the world, given we've fitted this with statistics, what kinds of things can we learn about the world by simulating it into the future. And this is the famous Phillips machine, now in the Science Museum in London. This is the scale for those of you who, this is the size of the thing with Phillips on the left and Newlin on the right. It's a large hydraulic machine. And this is an object which is both an inquiry into the world of the model. A lot of the reason for building this was to figure out arguments in macro at the time about the relationship between the accelerator and the multiplier, what the causal structure of investment, what caused investment flows and various interest rate issues. But it was also used to think about what kind of things might happen if you did certain kinds of actions. So it's also a model which was used to tell stories about the real world, to give you insight into the real world, or plausible stories about the real world, as well as to explore different kinds of theoretical arguments. Well, what does the capacity of those objects to reveal depend upon, right? They're very different kinds of objects. They reveal different kinds of things. I think what I want to claim about this is, well, the materials of the model does matter, but that's because different materials offer different experimental resources, right? So it's not that it has to be an artifact or any kind of model, but that these different models had different materials, or have different capacities to reveal things. They're in different forms, and they work according to very different rules, right? So going back, the materials of models does matter to the question that you're going to ask, because the different materials will give different experimental resources and teach you possible things about different aspects of the world. So the materials and the kind of questions you're asking have, in a sense, to line up. You know, you can't really tell sensible questions about particular values of things in the world unless you're in the statistical framework of Tinbergen. But Tinbergen's model doesn't give you many resources to explore Keynes's general theory. It really doesn't, because although Tinbergen built this as a kind of Keynesian model, it's not obvious where the Keynesian model is in Tinbergen's big statistical framework. Right? So it has to be an alignment between these two different things. Does the scale of the model matter? Does it matter that the Newton and Phillips machine is huge and Samuelson's little thing is very small? I don't think the scale matters, but the dimensionality matters. That's the number of dimensions that you've got there, which give you some possibilities. And I'm going to come on in a minute to this other question. How do model experiments compare with other kinds of experiments as a technology that reveals? So we thought about that one. Okay, so the different dimensions. I think one can think about it this way. Every time you've got something in the model that you can alter, that you can vary, is a possible dimension for being manipulated. Right? So If one thinks of Samuelson's little model, he's got 2 parameters, he's got fictional time, and it's in mathematical form. There's only 2 things he can manipulate in there. That's the alpha and beta in his Keynesian model. That's what gives him these dynamics, which mean that anything can happen. Tinbergen has something like 16 variables, each of which could be potentially things that you could think about controlling or altering or really investigating. He has real time represented in the statistical form. So he's got, if we count time, this extra 16 plus 1. Newland-Phillips machine has 9 controlling valves and a real time in hydraulic time, but not real time. Each has a time dimension that works somehow to map onto the economy, but none has the real time of the economy, because it would clearly be, well, you couldn't do it, but also it would be useless. It's just like the problem of having a map the same scale as the world. Right? You can't do that, but also it wouldn't tell you anything, because the benefits of maps to reduce the scale so that you can see things. So the time is a dimension, but it's not real time. It's a time which has to also be thought of as a manipulative variable. So if we go back to this this issue, right? It's the dimensions of possible manipulations in here also vary quite dramatically, and those dimensions are part of the machinery. So I don't mean to be mechanistic, but part of the stuff which can be worked with and which will offer potential revealing strategies. So I think the more dimensions, the better, in the sense of the more possibilities for learning when you work with the model. It's not obvious, it seems to me, what kinds of dimensionality you need. If you think about an alternative field, anatomy, a big step forward was to move from anatomical drawings of bits of the body to 3-dimensional models of bits of the body, right? And they obviously have different kinds of revealing possibilities. So it clearly does matter for some fields that it's a 3-dimensional object rather than a 2-dimensional drawing. I think in economics, very often we're concerned with time, forward possibilities of prediction, backwards when we're trying to explain historically why the Great Depression happened, why the financial crash of 2008 happened. And I put in sideways because it doesn't look like that's another dimension, but of course the use of models for counterfactuals is to run the world in another form parallel to the time that we've got. And that's actually one of the things that political scientists do when they're doing their counterfactual thinking. So I put in time as a sideways possibility. And the number of elements that can be varied. So I think they're important. It's relative to the question at hand. I don't think it's always obvious what the dimensionality of a model is. It's not obvious that Tinbergen has 16 dimensions that can all be independently varied. Right? There's 16 variables, but some of them are so constrained by the equations that there's probably not 16 dimensions of variability, 16 separate things that can be varied. Okay, so each experiment then has a different focus of investigation, these 3, different capacities to reveal answers, and about different things about the world in the model, about the theories that economists have, or about the events in the world. But I want to move on to this, really the most difficult question, as to how to think about the status of these answers that we've got here. So the reason I want to think about these uses of models as an experiment is because I think it helps to think about looking at the experimental outcomes, not just a final result, but the whole set of outcomes that comes from these process of experiment, not as a correspondence truth problem, right, where the model is an account of the world, what's true in the model clearly is or isn't true of the account of the world, but as an inferential problem, what can we learn about what by these experiments? And here's the sort of way I think about this in terms of other sorts of experiments. And typically the lab experiment has been taken to be the kind of experiment, the kind of classic experiment that forms the boundary. Although I think increasingly in econometrics, field experiments are forming the basic dimension for comparison. Lab experiments typically we think have high internal validity. That is, within the laboratory, one can get very definite results from a lab experiment. One might not, but one can. And the internal validity is based on the controls inside the laboratory, controls inside the experiment, the controls of the environment, and the controlled manner in which the experiment is done. So internal validity can be attested inside the laboratory. But actually it's very difficult to give an account of external validity which will hold in a general way. That is, how do you export your finding from the lab to the world? So this big problem of external validity, which philosophers and economists have been writing about, Francesco Guala, for example, but it really does, it is a problem for lab scientists. So when one thinks about lab science as being the main comparison, one should be aware that actually the external validity problem is not at all one that has been easy to solve or to kind of classify in a philosophical way. Model experiments, internal validity is obviously about the validity inside the world of the model, and for economists that usually means, you know, how do you set this thing up to give consistency in a sort of consistent set of answers and to have certain kind of characteristics. I'm going to talk a little bit about that internal validity an example, but here I think the world, the inference of the world is not an external one but a parallel one, because it's not as if we've got, in the lab we've got what we think are the kind of stuff the world is made of, and what we're trying to do is does it work out outside? Is it true externally as well as internally? Well, in the model you haven't got the real stuff of the world. In the economic model you've got a diagram or a maths or a map or something. So you're talking about not external validity, where you've got the same stuff taken out into the world, but something that you hope is going to happen in this parallel universe. The real world, which might or might not be parallel to your model. External parallel validity are both problematic, and I don't think there's an easy solution to either of them. And I think those both have problems compared to statistical experiments. And the wonderful thing about statistical experiments, it's not that they're necessarily always informative, but there's set rules for internal validity and external validity. Right? It may not be easy to get them to work, but the statistical framework is about creating inference rules about what you can infer from the sample and under what conditions you can infer from the sample of the population. That is internal and external validity. And they're both framed within the same statistical theory. So statisticians have a much neater way to think about these things, because they can think about both of them in their setup that they already have. Although it has to be said that although they might be really clear in terms of thinking about inference regimes, they may not be sufficient for action, and demography is a wonderful example. Demography is very descriptively effective, but it's not one that you can go and causally intervene with. Right? If demography is going to tell you how many school children you're going to need schools for in 5 years' time, but it's not, you can't use the demographic laws to go and change the birth rate. Right? So there's a sort of limit on what they can do. Okay. So back to the qualities. Okay, I've talked about manageable small representations, miniaturization, compression. I've talked about resources for investigation. I've talked about dimensions and capacity to reveal. And I want to come on to this last point, which is the most difficult to get to work, about this representative quality that Dastel and Gallison suggest that we need. How are we going to pass out justifiability as typical or exemplary in some form? What makes a model representative in some form for something? So in order to think about this representativeness, one needs to think about the class of things for which this is going to be representative in order to frame the inference space to the class of things that the model is going to be representative for. So models typically not going to be saying something about everything, but models are very often specified to be representative of a particular subpart of the economy. So a class of stuff that is in the economy. If that can work, if one can get that to work, I mean if, not philosophically, but if you're an economist practicing this thing, right, what you're going to get is something, an inference possibility which is wider than the experimental one, right? Because if you've got your experiment to work in the lab and you want to know whether it works outside, you may have to take it to lots and lots of different places to figure out whether it works outside. Right? Just because it works in the lab doesn't mean it's going to work anywhere, and just because it works one place outside doesn't mean it's going to work everywhere outside. So the model experiments, I think, have a somewhat wider range than the lab experiments, but they're much weaker validity. I mean, if your lab experiment works in the lab, you take it outside and it works in place X, right, then it's a pretty strong place X inference. Right? So it's going to be more particular and stronger for lab experiments, and model experiments is going to be weaker because this bounded place is not, as it were, real stuff that we can take from the lab experiment. So representativeness is going to give us possible inference range, which is wider than labs, but quality, which is less valid, weaker. So the inference range is associated with the typicality of the working object. So one can think of Darwin's finches. A type class in biology is typical for a set of finches and maybe typical for a wider class of animals, namely birds. I think that doesn't work nearly so easily for mathematical models because they're abstract working objects like mathematical models. The representing gap is just much bigger. Right? We can easily see how finches might tell us something, a type kind of finch might tell us something about the family of finches more broadly. But when you have a mathematical model, there's a big representing gap. And so one has to think about the quality of typicality and where you're going to find it. And here I think there's two bits. First of all, in relation to other models, and only secondarily to a class of things in the world that it might represent. And I think the first is about internal validity, and the second is about the parallel validity. Right? So inferring from an experiment in the world of the model to other similar worlds in models, right, is the internal validity, and inference from the model to the world that the model's representing is this wider parallel thing. Here I want to go back to Edgeworth, who in his first discussion of something which became the Edgeworth box, talked about something as a mathematical induction. And it's a very interesting argument he made that by virtue of a single representative, particular, authenticated instance of mathematical reasoning without numerical data, so it's an abstract mathematical object here, is sufficient to establish the general principle. Well, this is a pretty heavy-going kind of combination of things, but it's a very unusual for the time kind of way of framing what was going on, and this is the beginning when mathematical economists are beginning to start building models. So we're not talking here about the Walrasian general equilibrium world, which Walras was building at the same time, or built at the same time. We're talking about Edgeworth having produced a little diagram and making this claim about what this little diagram could tell us. Now, the single representative particular case, authenticated case, so we've done our little mathematical reasoning, we've agreed that this is perfectly sound mathematical reasoning. Representative particular is somehow a kind to capture that this particular model is representative for a particular class of things. And the class of things that Edgeworth was arguing about was exchange relations in the Robinson Crusoe, Man Friday world of isolated exchange. Now, if we think about the scope of the Edgeworth box and the kind of mathematical reasoning that goes on in it, one can argue that there's a whole series of moves by which these results just get taken from that first one, in Edgeworth's case, to the next one in Bowley, the next one in Pareto, and a set of people who created the Edgeworth box as we now, as economists now know it, so that the mathematical experiments, the representative particular mathematical experiments that Edgeworth did, don't have to be redone again by the next economist who comes along. They can just be transported from that first version of the model into the next version of the model. Right? And from thence, they can be transported into extensions of the model as the model develops and as the model usage changes. It's a bit unclear what the general principle might mean here. What general principle is he referring to? And I think one of the ways might be to think about this is to think about the way geometric reasoning kind of works. This is diagrammatic reasoning. And there's a very nice book by Reveal Nets on how Greek geometry reasoning went on, which is to say, this geometry looks like the complete deductive way of reasoning. But in fact, when you look at the way that Greeks developed the arguments, what they were doing is saying, let's take a point here and see what happens if we take that point there and we make an argument about that point there. Well, which other points is this true of? Well, let's take a next point next to it and see whether it's true. So it's actually a whole series of inductions, or kind of proof by boredom. How many of these points do you need until you're convinced of the general principle by which any point in this triangle, for example, would give you this kind of result under this kind of transformation? So I think that there's something here like a model induction. He's talking about a mathematical induction. I think there's a kind of model induction going on here, which enables the community to infer from model to model in the same domain, but then, for instance, when people change when economists move a kind of simple supply-demand model for a commodity into an argument about people's trade-off between labour and leisure, they're changing the domain of the model, they're making a model induction from the commodity space to the leisure and labour space. So something that comes with the model is a kind of internal validity about the reasoning that's already gone on in that model, which can be transferred not just into the sequence of the same model, but into analogical like models. And I think if you rethink now with this kind of framework, that's exactly what Samuelson was doing. He was trying out, first of all, different points on these parameters, trying out which ones worked, or what the results you got, found that they were all wildly different, and only then trying to map out the general space within which one could make these model inductions. So these are representative particulars here, which then he can't get into a general principle, so he has to figure out what the general principle looks like with a different mode of solution, but not because it's a different model. And the same is true if we think about Marshall's famous supply and demand curves. The representativeness here is somewhat different terrain. The representativeness here is that the world here, not the world in the model, but the real world here for Marshall, has different kinds of supply curves in it. Different industries have different kinds of supply conditions. Some have increasing returns to scale, some have constant returns to scale, some have decreasing returns to scale. And Marshall, I think under one reasonable interpretation, thinks that there's a whole lot of different types of industries in the world, and if you could figure out the different kinds of types and make a model for each type, you would have a set of models that would cover the terrain in the world. So that if you went to an industry and said, what's happening in this industry, and you knew which type of industry that was, you could then make sensible inferences about that type of industry based on your model for that type. Right? So it's a strategy which is like biology. It cuts up the world into types of things, and if you've got them all properly labelled and properly figured out, each of these models will give you the possibility of the parallel inference, or the parallel validity in that world. Right? So it's not that you've got a general supply and demand model, you've got always classes, types of models which might or might not apply. So the representativeness here is not in the world of the model to the next generation of the model, but each of these models is representative for a type of industry or type of firm. So the representative is going to the parallel validity problem. Okay, I'm getting towards the end. You're going to be pleased. 3 more slides. Right, so of course this parallel validity problem is not without its difficulties, because some of these things might not exist. They might be empty. This is the classic argument. Well, the analytical worlds in the models may or may not act as representatives for types of phenomena in the world, because not all of those types might exist. It might be the case that some of these things they don't have any equivalence in the world. Right? We've made them up in the world in the model, and there's no reference point. There's no industries which fit into that, which is the argument of empty economic boxes. There are no industries of some of these kinds. So if they're not empty, if these representative particulars are, each representative particular is not an empty box, then it might be that you can expand your inference from the world in the model to the world that that model represents in a representative way. But it's going to be very restricted to just that class, not to everything else. It's not going to be a general inference, it's going to be restricted. So that's why I say it's not a generalizable inference, it's restricted, it has a space of possible inference, right? It's got a broader range than the lab, but it's quite vague. These are quite vague. There's no numbers on them, right? So all they've got is directions. So it's vague, and it's restricted to the class, but still it has that possibility of the inference space, right? Broader than labs, but vaguer, if that's the right way of expressing it. And not generalizable beyond the class for which this is a representative case. So, yeah. Models may be truth makers about the small world in the model. That's the internal validity argument. If you can make this world in the model, it offers you has revealing capacities, has dimensionality, it can make you truths about the world in the model. But not about the world that model represents necessarily. So the outcome is that learning about the models learning about the world from working with models, if we consider it as an inference problem, it's going to invite modest claims about how much we learn about the world from models, and deep skepticism about action in the world based on models. So we should be worried about using models as engines, not cameras, as in McKinsey's firm. Now, okay, so you say, we know all this already. We know the bottom line. We know that you can get these nice little results in the world of the model. We know it's dangerous to think that the models are going to tell you things about the world. What I've been trying to do here is to say, yeah, but at least now we've framed it as an inference problem, we've managed to get some space in which we can see why some inferences may be plausible and helpful, and why some of them are not going to be going to give us any kind of outcome. But even apart from that, we've also got some grip on how it is that models are going to have these revealing possibilities about the world in the model, which might tell us about things we should be looking for in the world, which we wouldn't necessarily have thought about looking for without this experimental framework. Thank you.
Complete, enriching, clear, decent out. Now, time of questions.
I want to ask you about the truth problem, or the truth. Just a small problem.
What do you want to ask more exactly?
One of the options, the last one, about models, maybe truth makers.
About the world in the model.
Yes. And that is all, or you can extend.
That's the only place I think where I have truth in these presentations. It may have slept in somewhere else, but actually, no. There's nowhere else you can make truth in this framework, except in the bound, it's the internal validity, but the internal validity may not tell you anything about anything that's interesting. Right? I think that's true of the Samuelson. The Samuelson model is very interesting because it tells you that this model is totally inadequate because anything can happen. Well, a model in which anything can happen is giving you some truth, but it's useful to know that, but it's not going to be much use anywhere in the world.
Nicolas. Well, in English it's difficult, but
well, you could try it in Spanish and get someone to translate.
Yes, my worry is about the relation between the models and the real world. And you use the the parallel validity, different with the lab, the experiment of the lab, but that external validity.
Yeah.
I remember that Cartwright used external validity in two cases, and when you say parallel validity, I thought in Sugden, that Sugden,
credible Sugden.
Sugden used parallel and induction, and these two, Sugden and Cartwright, have two different views of the relation between the model and the real, and which is the winner? Oh, which is?
That sounds like a truth question. Okay, so I find it useful to distinguish between parallel and external because I want to make this point about how limited lab experimental inference really is. Because I think people don't appreciate how limited it is. You know, that how really, if you know that you know something about, you know, you've done this experiment in the lab, you've learnt something, you've repeated it again and again, and you're sure it's true. And your truth making, I mean, again, truth making within the world of the lab is the same kind of problem. You may not get it the first time, but after many repetitions, you might get it. And then in the world which is not in the lab. So I don't think a lot hinges on me calling this parallel and her calling this external, except I wanted to make the point about lab science versus model science.
So the relation between the models and the real is more difficult than between the labs and the real world.
I actually think they're both difficult. I mean, I think my father was a lab scientist, and I learnt from him that, for instance, you know, I mean, a whole lot of objects go from, you know, solid to a liquid to a gas. But if you actually want to use one of these things, you've got to go and chart out exactly the process and the time and the temperatures and everything else. So there's a generalizable kind of finding, which presumably took many decades to establish that this was true in a very general set of class of things. But it still doesn't mean that you don't need to know the particulars for that particular thing if you're going to use it somewhere. So I don't think that the lab experiment external validity, I mean, it's not philosophically easy, I think, to frame, and I think there's interesting work by Dan Steele on this, and interesting work by Francesco Guala in the case of economics about the kind of reasoning that would get you there. But so all I'm trying to do with the different terminology is say it is slightly different here, it's parallel. Now the Sugden case, Sugden, I think, uses it for a different reason, which is he wants to have these agent-based models outcome. Somehow he wants to be able to get the outcomes of those kinds of model experiments directly mapped onto the world. So without actually figuring out any of the causal structure that would actually get these outcomes. So I think that's a different reason for using parallel, because he thinks of them as, you know, these parallel worlds, right? So that's, and I don't really, it's the same problem. I don't think his solution quite gets us there. I don't think he can do quite what he's saying, but it's the same kind of idea. Yeah.
Okay.
I don't think the model is a very, very expensive notion.
Yeah.
There are other things or concepts, the methodological importance that are not models. All is model.
Sorry, all his models.
All is model, or there are other things or concepts that are not model.
In economics. Yeah. What do you have particularly in mind? Data? Facts? Theories?
Facts.
Yes,
and the difference theory and model.
I think it's really problematic now to figure out where the line lies. You know, economists will talk about the law of supply and demand still, although to all intents and purposes that's a kind of very generic, general sort of stuff, which as soon as they want to do anything with it, they're going to start talking about models, right? And then there's the quantity theory of money, which is kind of proper theory, which, you know, has a thesis about causality, and it's supposed to be general and whatever. And then there's things like game theory, which is a whole approach. So I don't think there's a good line for economists between theories and models. And theories might be somehow a little bit more general, a little bit more hypothetical. I don't think it's easy to say. I tend to think of Walras having a theory and Marshall having models, because it's something about not the scale that's mattering here, but the method of approach in which the Walrasian world is one in which there's the whole everything is postulated, and then it's a problem of solving this in a kind of hypothetical postulation and proof regime. And I think of that being different from models, which is this workable sets of instruments, tools, and I think of them as different because of the work of Hacking and Crombie on epistemic genres, which separates out historically the development of mathematics, the method of postulation and proof. You postulate something, you prove something. Again, truth in the world of mathematics, from analogical and hypothetical modelling, which has its roots in astronomy and those little mechanical models which people turn the handle of and see the planets going around, which is not postulation and proof. It's a modelling tradition. So I think there are two traditions, both using mathematics, which makes it difficult historically to pull them apart.
Would you say that there's any kind of quality that a model should have in order to predict the future, reality? Or would you say that a model that has more variables and parameters are more useful to use it in practice, reality, or?
Is this about the scale and the dimension problem?
Yeah.
Yeah, it depends on the purpose, right? I think at one stage central banks just had large macroeconometric models, and I think more recently, I don't think there's anybody from the central bank to tell me what their models, but at a certain point, maybe 20 years ago, maybe 15 years ago, a lot of them gave up these big models. So they have a short-term forecasting model, which is basically a time series descriptive model. For a particular purpose like forecasting, they might have a descriptive short-term model. For other kinds of issues like thinking about growth in the economy and the role of money in growth in the economy, they're going to have something like a macroeconometric model. They're going to have a whole suite of models designed for different purposes and speaking and being used for different purposes. So it's not that I think one model, the larger the model, the more things you can do with it. No. It's about the relationship of the dimensions for the questions you have, but given the question you have. So, for instance, to go back to the Sugden, keep forgetting what this thing's called. These agent-based models, right? So the model he's talking about is the Akerlof model of Schelling's model of prejudice. A simple low-level prejudice will give you the housing distribution that we observe in the world. Well, the problem for me, that may be entirely predictive, but we don't have any numbers on it that give us a relationship to the world, so we can't take a neighbourhood now and tell you how many years it's going to be. Maybe you can now, but that if you want to know about people's movements, for some questions, you'll need to know about the causes why, the full set of causes why people move. Larger families, smaller families, deaths, divorces, new jobs elsewhere, all of those reasons we know people move for in order to be able to get a grip on exactly what's going to happen to particular neighbourhoods. So for you need to know the purpose, and then you need to know the dimensions that are relevant for the purpose, and it might be more or less for the purpose.
But if you want to know something that requires a lot of causes, shouldn't you consider all of those causes?
Yes. If you want to know a good causal structure,
isn't that a contradiction? Using a model that has that is small, that
No, it's all relative here. I just mean manageable, right? No, so of course, in this case of the housing, right, there might be 100 causes, but actually we already know that there's maybe 5 or 6 that are really important ones, and they're going to give us 98% of the statistical variability if we were to do the econometrics. So we'd be under then to say, okay, there's an extra 2%, but it's so minor that it's not going to make much difference.
Let me tell you first that I enjoyed very much your presentation and your vintage examples. Very nice. I come back to the question about model and theory.
Yeah.
There are some models that I can think of them about as abstract representation, and there are other models that I can think of them about parables, as states. Not exactly. The Warasian actioner is a change, it's not a theory, it's not an abstraction, it's an invention. I think it's a good invention for some purposes. Now, if I don't have a theory back, I am not sure I will be able to grasp if this model is a parable or is an abstraction.
I think, okay, an abstraction is a thing, and a parable is a story, right? Has action in it. So from my point of view, an abstract object like a mathematical object, when it is used with these experimental frameworks, you don't just have the abstraction, you do something with it, right? You inquire into what's happening in this world. And it's in inquiring into what happens in this world that you end up giving stories about models. So if when you go to an economic seminar, people will say the story would be, right? So for me, the parable or the fable, depending on how you want to play this one out, is actually related to the use of the model. So I don't think in my accounts, you can't have an abstraction or a parable. A parable or a story or a narrative is something that comes as part of the way that the outcome, the process of the experiment and the outcome are related to events in the world. So, yeah. So we've got an abstract model here on the left. In manipulating that model with certain questions, what happens if we increase G by 1 unit, we get a set of outcomes. And those would be, we then start saying, oh, look, if the parameters are this, we're going to have an exploding world. So there's going to be a story account that's going to come out, and we pretty much know that we're not going to be in that kind of world, so there's kind of a parable if ever there was one, right? But, so this is not a plausible kind of world that we can be in. So but this is a very simple model. There's a Mead model, a model by Mead, which has 8 equations, and immediately you get to a slightly more complicated model when each time you change one thing, lots of other things change in the model because of the interactions in the model, and each of those can be mapped to things that might occur in the world. Right? So there's going to be narratives that will map or not map onto the world. So the parable is one of the ways in which the outcomes of experimenting with the model is a mapping onto the possible ways in which this thing fits the world. So for me, these are not, you can't have one or the other kind of model because they're models which when you use, you tell narratives, and one can conceive of those as parables or fables, depending on how one wants to think about the model.
Thank you. I have 3 questions. First is, how about, I think that the way, there's not a uniform way to represent time in economic models. Do you think that this can be a kind of important issue in order to critique economic models because of their lack of realism? First question. I don't know, maybe I'm wrong. Second is, how important are assumptions before modeling?
Pencil. I'm looking for a pencil because she's going to 3 questions. Sorry, thank you. So the first one is time.
The first one is time. The second is, how about assumptions before modeling? Which is the role of assumption? It's, again, there is a kind of uniformity on this issue. And the third question is, if we are using models, as Mackenzie suggests, as cameras and not as engine, there can be a dangerous side effect that the models are just rhetorical tools. They are not describing. They are persuasive or not.
Okay, so I never think that things are merely rhetorical or just rhetoric. I think the performativity thesis is really interesting. I think absolutely what's happened with economic models is that they have become performative, that they've become, as you pointed out, part of the way that we think about the world, not just us as economists or philosophers, but in the users of people in the world who use some of these models, which is what the Mackenzie point is. The whole point of the Mackenzie is that they are not rhetoric and persuasive. They come with artifacts on which people act. So the Mackenzie argument is not that these aren't cameras which we make pictures of and people say, yes. They are objects which create pieces of paper on which people decide to take action and take actions and therefore trade. So the performativity of models is a really important point to notice. And of course there's lots of ways in which models are performative, used by governments for all sorts of purposes. When they're used by the population more broadly, then they also going to have consequences. The assumptions issue, yes, of course these assumptions are highly unrealistic, but I always think that's really not the point. That the whole point at the beginning of the talk was to say, this is not, a piece of mathematics is not the world. But the as-if assumptions about people's behaviour is only one of the problems. Right? How do we know God made the world, the economy, to be mathematical? We don't. Right? So it's the language of representation which is a gap. There's these as-if assumptions which, are, broadly speaking, we know as economists that people don't behave like this, and there's all sorts of economics in the last 20 years which is about how they do behave. There's a large chunk of economists who think we're never at an equilibrium, we might be tending to one. Right? But the point about this is, okay, you've got these models, that's the as-if assumptions is only one way in which you're going to think about them. Right? The as-if assumptions generate certain kinds of behaviours. Sometimes they really grip strongly, as in game theory, sometimes they don't. Some of these as-if assumptions don't have a lot of power. I mean, just think of the utility function. We're going to maximize this utility function, but we can put anything to that utility function. Right? So I always think it is a kind of straw man in a way. So the as-if assumptions is one set of things. There's the medium the model is made in, which is another point, which I think is really important. The statistical models we have some reason to think the gap might be not so big in the representing form because these statistics are measurements of things that have happened in the economy. Right? But I think that the issue about the experiments and the narratives are that you have a whole of what-if questions, and each time you ask one of these what-if questions, you get a set of answers which you need to map onto the real world. So as-if is important, but it's only really one of them, and if we jettisoned all of models because the as-if doesn't work, then we're in the same situation, it seems to me, of saying, well, maps are no good, poetry is no good, we have no insight from either. Because that's the only one bit of it, right? Time. Yeah. This is the benefit of the bottom right, is that it represents time in a continuous form. And I think time is an underappreciated aspect of modelling, and I think particularly the kind of macro models is very dependent on national income accounts, which are quite rigidly time-based in ways which may not always be very helpful to the kinds of events that we are working with. So the moment in which national income accounts became available quarterly made quite a big difference to the way models worked, because it moved from a whole year down to the quarter, and it gave a lot more possibilities which you couldn't do with the original models.
Ronald here uses the concept of hypothesis to make a connection between models and reality. Your use of fables or stories is similar to this concept of hypothesis?
I think that you can think of the hypothesis in the same kind of experimental tradition. You know, hypothesize something in the model, muck around with it in the model to see whether or not it's true. That's like the lab experiment. We hypothesize if we do X in the lab, this is going to come out. That's the same kind of a framework. I think the issue of you know, and it also can map onto, you know, so the mapping onto the experiments is one part of it. But I think the hypothesizing something doesn't point you towards the action and the interpretation. It points you to say, I've hypothesized X, is it true? And I'm trying to get away from, this is the way that one should think about models. Because you really then restrict it to the notion that models are for hypothesis testing. And that seems to me not a very good place to be, because a lot of what models are used for are not hypothesis testing, but hypothesis formation, exploring worlds of models, exploring possibilities, and hypothesis testing as hypothesis and then hypothesis testing closes down the way we think about what models are doing for us, could be doing for us, might be doing for us, but not necessarily doing for us. No, I'm okay. Yeah.
I probably didn't understand very well when you say that the scale doesn't matter.
Oh yes, scale doesn't matter. One should never say things like that, should one?
So this is my first question, that is almost quite clarification on what you say that. And the other question is on the issue that the data facts that we work as economists, you came from national statistics, surveys, pressure data, like custom data, you know, so I wonder how much this kind of sources of data impact on the way that we model.
Yeah, two really good questions. Yeah. Okay, I cut this out because I knew this was already too long. I've got something about scale. Right, the top two bits here. Scale does matter, but I think people think scale is just a matter of scale. Okay, if you have a scale model in natural sciences, they're typically not simply a scale model, because you have to change the materials to get the right qualities. So there's a very nice paper by Naomi Oreskes about earthquake simulation models before you had computers, right? And so you create a little wooden box, and you can't put rock in the box to shake it, because you know the rock's going to not do what you want it to do. So you either put something like sand or wax or pancake batter. Pancake batter translates? You know, in order to get the right qualities for the scale, right? The other example I know of is some work by Susan Sterrett on deep sea cables, the cables, transatlantic cables, telegraph. So when they were exploring how the qualities they needed for the cables, they had to not only change the metallic content, but the seawater had to be made more viscous to get it to work. So my point about scale is not that scale doesn't matter, but that we shouldn't necessarily think of scale models as being different from other kinds of models, because a scale model typically changes the materials. So it's not quite the same thing as having the real stuff in the lab outside the lab. Wind tunnels probably have the same kind of problem. You know, you probably have to have a big enough wind tunnel to get the right effects, and if it's too small, it probably doesn't work, I suppose. I'm not an expert on wind tunnels, but I suspect that the turbulence properties don't work until you have it a certain size. So, yeah, I don't really mean that it doesn't matter, but clearly scale and dimensionality is related, but I think the materials issue is what I was trying to get at. Yeah, the sources of data, I think this is a really interesting issue, and I think it's very evident at the macro level, because all of the macro stuff depends on these national statistical offices until about 1950 or thereabouts, quite a lot of economists collected their own data. At that point, most economics input into data design, data gathering, comes through committees on which economists sit. So if you want to change your consumer price index, there's probably going to be a couple of economists sitting on the committee deciding. But I think more recently, again, economists have got very involved in designing surveys on which statistical data comes, and I think the quality of the data can then be the design of the collection of the data then has implications for the quality in order that it maps more closely with the kind of models. So I think it's a very important point, and it's quite difficult to generalize about exactly how it impacts, but I'm sure you're right, it does. Yeah.
Well, again, thank you. I don't know if the question mark, I'm a little confused in this point. In all my career, I study economy, and when I all my career, I study a lot of models. All the subjects are the knowledge I receive, and I study models. When I finish and I start to read maybe the philosophers of economy, I know that it's a very important problem between the relation between the models and the world. I know it's confused, study models and then no. It's a problem. So maybe the question is in your view, and if the activity of economic activity is in a good way or not so.
Be skeptical. Look, this is another one I didn't show, but right, models often don't work in the world, but not only because you've got a bad model, right? Not just because you've got a bad representation. There's a whole lot of other reasons why your models may not tell you very much about the world or may not be very good for acting in the world. For instance, it's descriptive, but doesn't give you access to causes, but the descriptive models can be really useful for some purposes. The ceteris paribus conditions don't hold, that seemed perfectly reasonable when you wrote them in the model, don't hold in the particular place you take the model to. You get plausible explanations, but there's no recipe for intervention, right? So you get half of, it's not the same as description. It can suggest modes of action which are just inconsistent with something else that's going on. So however much you'd like to stop people smoking, the government wants more money, so it changes the tax rate. Which one's it going to do? It's not updated. We don't, this comes back to the data problem. Particularly in the macro field, a lot of the feedback is pretty slow. And if we're trying to do real-time interventions, we're always behind the curve. And that's why a lot of macro data gets revised for the next, I don't know, this country, at least 3 years in Britain, but I don't know what the average revising time is here. But, it can be revised again and again and again. So there's a whole lot of reasons why, and there's an etc. there, things I haven't thought about or written on or something.
You have quoted a poem in your presentation.
Yes.
In one of your slides. Considering that quotation, what is the place or the role of beauty in the clarification of models?
Beauty is in the eye of the beholder, I believe. Yeah, so there is this interesting strand of elegant. Its beauty is sort of more elegant, I think. The usual expression for economists' models. And I think that's actually more interesting than beauty, because I think it's something about the ability to be quite expressive, to be quite articulate in a clean way. So that's partly why I think the poetry example is quite interesting, because it's about the articulability within a minimalist kind of way, but which still has these formal properties. When you look at sort of the models that economists talk, when they talk about each other's models, and they talk about people who produce models which they find elegant, typically the ones that are elegant are ones that then get picked up and used and have a longer lifetime. So the elegance is associated with a kind of longevity. Right? So it's almost a kind of post hoc rationalization. You know? It's not necessarily evident as soon as the model is there that it is an elegant model. Maybe people recognize it's really neat and smart, but part of it is about this ability to kind of have a longer life, I think.
Well, thank you very much.
Thank you.